Welcome to The Explainer. Today, we're going to pull back the curtain on a concept that is absolutely fundamental to writing great, scalable code: Big O notation. If you've ever wondered why some of your code just flies and other parts seem to grind to a halt, well, you are in exactly the right place.
So let's kick things off with a scenario that I know you've run into. You build a new feature, and with your test data, a handful of items, it works perfectly. But then it goes live, and users start throwing thousands or even millions of data points at it, and suddenly your application just crawls. This isn't just a simple bug, it's a scaling problem.
So here's our game plan for today. We're going to start with the what and the why of Big O. Then we'll get really practical and look at how you can actually calculate it, use it to compare different solutions, and see how these choices play out in the real world. By the end of this, you'll see exactly why understanding this is a true developer superpower.
All right, let's dive right in. The reason code speed matters at scale isn't really about raw seconds on a clock. It's about how that performance changes as the workload gets bigger and bigger. And to talk about that in a standardized way, we need a specific language, and that language is Big O notation.
So what does that actually mean? Well, to put it simply, Big O gives us a shared vocabulary to talk about how fast or slow an algorithm is. It's not about measuring performance on one specific computer, which can vary wildly. It's about describing the inherent efficiency of the logic itself. And this is the key thing to get your head around. We are not timing our code with a stopwatch here. Big O could not care less if your function takes 5 milliseconds or 5 seconds on your laptop. What it cares about is the trend, how the number of operations grows as the size of the input, which we'll call n, gets larger and larger.
Okay, so this slide here shows you the most common growth rates, kind of like a leaderboard from best to worst. Up at the top, you have O1, or constant time. That's the dream. Think of just grabbing an item from an array by its index. It takes the same amount of time no matter how big the array is. Then you have O and N, or linear, which is pretty good. It just means you have to look at every item once. But as we go down this list, things get nasty. O(n squared, which you see a lot with nested loops, gets slow fast. And once you hit exponential, forget about it. The algorithm becomes totally unusable. So our goal as developers is always to stay as high up this list as possible.
So let's see how this actually works in practice. How do we go from a piece of code to one of those O thingies? Well, you start by thinking of your code as a function that just counts the number of operations it performs. If you've got a complex bit of code with multiple loops, you might end up with a messy formula that looks a little something like this. Now, this function here represents all the hard work your algorithm does for an input of size n. It looks complicated, right? But the beauty of Big O is that it's all about finding the one part of this expression that truly matters as n gets huge.
And the process for simplifying this is actually beautiful. It's just two simple rules. First, you look at all the terms and you find the one that grows the fastest. I mean, as n gets to 1,000,000, n to the 4th power is going to absolutely dwarf n cubed. That's your dominant term. Then, second rule, drop any constants. The 6 out front, it doesn't really affect the rate of growth, so we just get rid of it. And what you're left with, that's your Big O complexity. Simple as that.
Okay, so we can do the math, but why should you even care? Well, this is where it gets really interesting. This is where Big O stops being some abstract theory and starts being a powerful tool that helps you make smart decisions. Let's use it to compare different ways to solve the exact same problem.
Just take sorting, something developers do all the time. This table shows that the algorithm you pick makes an enormous difference. If you go with selection sort, you're stuck at O(n squared no matter what. That means if you double your data, your work quadruples. That's a bad deal. But now look at merge sort. It chugs along consistently at O(n log n, which is a much better place to be.
And this right here just brilliantly illustrates the impact. For 10 items, you won't notice a thing. But for 1,000,000 items, an O of squared algorithm might take hours, while an O of n log n one could be done in seconds. This choice is absolutely critical if you're building apps that have to deal with real-world amounts of data.
Let's take another classic example that really hammers this point home: generating a Fibonacci number.
So a very common first attempt is to write a simple, brute force recursive function. But as you can see from this diagram, for just fib of 5, it is incredibly wasteful. It's just doing the same work over and over again. We're calculating fib of 3 twice, fib of 2 3 times. The work just explodes outward.
And all that wasted effort?
It leads to an exponential complexity of O of 2 to the n. And let me tell you, that is a massive red flag. Any algorithm with this complexity becomes completely useless for even pretty small values of n, like say 40 or 50. It's a textbook case of a solution that looks elegant but completely falls apart at scale.
Okay, enough theory. How does this actually show up in the code you write, every single day?
Let's bring this right into your code editor. You're working in Java, you need a list of something, and so you type list, myObject, list equals new, and then you pause. What comes next? As we're about to see, that choice you make in that moment matters a whole lot.
So you're faced with two of the most popular choices in Java, ArrayList and LinkedList. And under the hood, they work in totally different ways. An ArrayList is basically a smart array, which makes it super fast to get an element at a specific spot. A linked list, on the other hand, is like a chain of nodes pointing to each other, which makes it really efficient to add or remove things without shifting the whole list around.
And as this user on Stack Overflow points out, for most of your general, everyday tasks like adding stuff to the end of a list and then looping through it, ArrayList is your go-to. Its performance is just a great match for those super common operations.
But, and this is a big but, here's the crucial distinction. If your specific job involves constantly adding or removing items from the very beginning of a massive list, an array list would be awful. It would have to shift every single other element every single time. And in that specific scenario, the linked list's O of 1 constant time insertion makes it the undisputed champion.
And that's it, right there. That is a perfect everyday example of thinking in Big O. You don't just pick a data structure at random. You think, what am I going to be doing most often? And then you choose the one with the best time complexity for that specific job.
So you can see, this isn't just some abstract thing you cram for an interview. It's a genuine tool, a fundamental part of your developer toolkit. Let's boil this all down into the key takeaways that really make this your developer superpower.
So what are the big things to walk away with? First, remember that Big O is all about scaling. Second, the math is easy. Find the fastest growing part of your code and ignore the rest. And most importantly, use this as a design tool. Think about these trade-offs before you start coding, because as we just saw, your choice of data structure can have huge performance implications down the line.
And really, this knowledge is your superpower. It completely reframes how you approach solving problems. You'll stop asking only, does it work? And you'll start asking the much more important question, how well is this going to work when it really matters? And that, right there, is the mark of a truly great developer.